Okay, well, welcome back. Hopefully everybody had a relaxing holiday and you know got your assignment two in, preferably before the break or after the break, I guess is fine. But um, all right, so assignment three has been released. Just a few details on that. So I haven't released the solutions to assignment two yet, but I will probably right after this class. So the idea behind assignment three is that you're going to take all of the classes that you made for assignments one and two, and you're going to combine them now, right? So we have a bunch of redundant code, and that's sort of one of the things that, well, redundant code you can always fix by making a function or making a class or making a superclass. And so we're going to make a superclass. We're going to restructure our existing code so that it all works together. And then you could do things like put a text area in a panel or put a panel, put a panel with an absolute layout into a panel with a flow layout, and you can combine all of these components together whichever way you like. So that's the idea behind assignment three, and then you will make a UML diagram that sort of describes this design. Now, I give you a specification, but I am really okay if you sort of make some changes to that, as long as, the test code still works. And then, yes, so you're going to make a UML diagram, and then the other thing you're going to make is a linked list. So you're going to take one of your, let's say, your text area array class from assignment two. You're going to take that public interface, all of those publicly facing functions, and you're going to keep that interface, and you're going to rewrite the back end to use a linked list and also to store components instead of text areas. But otherwise, the publicly facing interface should be the same. Now, a word about that for tutorial 6, right? So that's due this weekend. There is sort of an easy way to get it done because if you just take the text area array class and you change all instances of text area to component, right? You just do a find replace on all of that. That's going to work basically the same as we want the linked list to work. So you can use that for the tutorial and pass the tutorial and get your grades, right? For the assignment, a TA is going to look to make sure that you've done a doubly linked list instead of an array-backed list. But for the tutorial, that will pass. So for the tutorial, all you need to do is make a component class, which is it's the base class that we'll be using. It should be somewhat simple, and then take that text area array class and make a component list class that does basically the same thing. And that's fine. You'll get the marks. Nobody's going to check and take a look to make sure that on the tutorial that you've used a linked list. On the assignment, if you don't use a linked list, you'll be deducted marks. But that being said, it's better to lose those marks. If you can't get the linked list going, you still have the backup of some array data structure that works, and that's fine. If the tests still pass, you get those grades. You'll just lose the marks for the linked list. All right, tutorial 7 has not been released, but I expect that will be shortly, probably today, depending on how much time I have. But, all right, so that's essentially where we stand. Any questions? Okay. So we had left off talking about, I feel like I'm forgetting something. I don't know, man. I'm still in like vacation mode. So if I forget something, please remind me, but did I record this? Yes. All right. All right, so we were talking about inheritance before the break. And we have basically gotten this far, so not very far at all. So when I'm talking about inheritance and object-oriented programming in general, I'm going to peel back the curtain a little bit and do something probably different from what most people do. So we do have a tendency in computer science to really rely on abstractions, especially when you're teaching computer science, right? So the idea, what happens is that, well, abstractions are great. We use them all the time. So like any programming language is an abstraction because it's not really running that programming language, right? You have to, C++, it has to compile into assembly code, and then that assembly code is translated into machine code, and then that machine code goes into the CPU. But all of that complexity is hidden away behind a nice language, right? Or arguably a nice language in C++. Yep, for sure. So yeah, we've talked a little bit about abstraction layers, and object-oriented programming is an abstraction layer. Abstraction layers are great if you're unskilled, but as a developer, well, the problem with abstraction layers is they're leaky. Abstractions are always leaky, which means that the underlying implementation gets through, and it's helpful to know what the underlying implementation is, because at some point as you're writing to your abstraction just using C++, it's not going to behave the way that you expect. And at that point, it's going to be useful to understand what's going on under the hood, so to speak, right? So abstraction layers are great because they reduce cognitive load. This idea that you should just completely ignore what's happening underneath them, I disagree with. I think you should understand what's going on beneath the abstraction layer, because they're always leaky. There's no such thing as a perfect abstraction. So I am going to be sort of peeling back the curtain a little bit and looking at a very low level as to what this, what is inheritance, right? So we're going to see that it's a lot like composition. Right? When you get right down to it, when you compile C++ down and you have these inheritance hierarchies, what you get is kind of a bunch of structs that are inside of other structs. So we're gonna focus a little bit on that. All right, so what is the role of inheritance? It's another method of abstraction and encapsulation. A big deal is made of this is-a relationship. So we're going to talk about what this is-a relationship is. I know in an abstract sense, you know that a sailboat is a boat, right? But what does that mean for my classes? What does it mean for my sailboat to be inherited from boat? And in this case, it is a boat. What does that mean? Well, in C++, of course, the preferred syntax or the preferred vernacular is base class and derived class, but we might also say parent and child or whatever. There's probably some other ones that I'm not thinking of. Well, in C++, when a sailboat inherits from a boat, and this is, let's say this is probably what it does, right? Because C++ is just a specification, so what your compiler actually does is up to the compiler, as long as it behaves this way. But this is a good memory model, and it's going to be correct most of the time. So when I make a boat, right, well, the data of my boat is stored in a sort of a boat struct type thing, and it has a single int, which is called capacity, so all the data in my boat class is stored in 4 bytes. And then I make a sailboat that inherits from boat, and then I add a number of sails, an integer, and a float that describes the speed of the sailboat. And then those also get stored. And if I look at what is happening, well, I have an instance of the boat class inside of my sailboat class in terms of where the data is stored, right? So it's a lot like composition. When you compile it, you basically get composition, right? So I could, and we're actually going to show this, but if I wrote this a little bit differently, and actually I used struct here, but I don't even really need to do that. I can still use class because they are the same thing in C++. Here I'm not using inheritance at all. I have a boat and I have a sailboat that contains a boat and also a number of sails and a float and a speed variable. And it just so happens when I look at how that is laid out, it's exactly the same as, right? So we're going to use this analogy of inheritance is a lot like composition so that we can, well, because it is, and also it's going to help you to reason about what happens when you do things like have a giant inheritance hierarchy, for example. All right, so inheritance and composition are alike in a lot of ways, and one of the ways is that we do have to take into consideration member access. So access modifiers, public, private, and protected. So just because we inherit from a class does not mean we get full access to that class. And in fact, the way in which we get access is a lot like if we use composition, as we'll see. So, sorry, we're going to make, I'm going to do a little very rough UML here. I'm going to have an animal, and I'm going to have a chicken that inherits from animal. And this is the rough structure of our inheritance hierarchy that we're going to play with here. And so here I have my animal class, and I have a lifespan that's a float that is protected. I have two private members, string and age, and of course I have a constructor, destructor. I have a public getter, we'll see that'll come in handy, and I have a public print function. And if I go to here, well, I can make an animal, and then I can print out that animal. So my animal is called Alex. And there we go. So animal, Alex is an animal with age 8 and a lifespan of 12. And we can see animals created, animals destroyed. All right, so now we're going to inherit from animal in my chicken class. So I'm going to do this in all of its detail to start with. So class chicken, colon, and then I'm going to publicly inherit from animal, right? So as we will see, there is public, private, and protected inheritance, but of those, public is the one you're probably most used to, and public is the one you'll use the most. Public is classical inheritance. Private and protected are something different. Of course, my compiler does not know what an animal is, so I'm going to help it out by including the header file. Okay, and all right, so we're going to have a public area here, private area. So I inherit a bunch of stuff from animal, but what I also want to have an egg count, right? So my egg or my chicken lays so many eggs per day, and I want to keep track of that. In addition to that, I want my I want a constructor, but now my constructor for chicken is going to be, the one that I'm going to be using. So I still want to initialize all my animal member variables. Make sure that I take in all of that data, right? So, and then in addition, I want my egg count. And I'm going to use a little bit of poor design here. I'm going to put all my implementation into the header. So this is what age equals 0. This is lifespan equals 0. And then I have everything I need to make my animal. So chicken inherits all of the member variables of the animal class. So that is the lifespan, the name, and the age. And in my constructor, of course, I want to initialize those. So if I did something like this, name equals name, well, of course, this is inaccessible. So even though I inherit from animal, I do not automatically get access to its member variables. This is private, right? This name variable here is this name variable here, and it is private, so I do not have access. So I can't initialize it directly. I can make a setter or something like that, but let's ignore that problem for now. Age is the same thing. Age is private. This is for my lifespan. Well, let's see, lifespan is protected, which means I do have access to lifespan in the child of my animal class. And of course, my egg count, I can initialize like this. I could also use member initializer syntax, but this will do for now. All right. So let's go back to main. Let's make a chicken. print a chicken. Oh yeah, I need a default argument. Since everything else has a default argument, my egg count here, let's say, is 5 by default. Okay, so I made an animal, owl with age 0, lifespan of 10. So yeah, that's really, it's still printing like an animal, right? So I can call print on my my chicken, but it prints like an animal. Let's have it print like a chicken. Let's make a void print. And now, again, I have the same problem of access, right? So I want to, for instance, print out something similar to this. And then I want to add some stuff to it. So if I said cout and is a chicken who lays egg count eggs per day. Okay. Well, that works, but this is not working, right? So not having access to these private members is actually causing even more problems in my other functions. So I want to print out my chicken parts, but I also want to print out my animal parts. But I don't want to violate encapsulation, right? Those are private. I want to keep them private. So I want to call print, but I want to call the animal print, right? Because, well, I mean, if we're obeying the rules of encapsulation, there are public ways that I can interact with this class, right? Even though I inherit from it, I can still only, I get the public functions as well. I get the protected ones too. But in particular, I can call this print function, but not directly because I've overridden it. But I can call it indirectly. I can tell the compiler, hey, look, don't call this print function, because if I call this print function, I'm going to get an infinite loop. But go ahead and call the animal print function. So I use the scope resolution operator to say, like, hey, there is a function called print. You'll find it in the animal class. Please go and call that. Okay. And that's nice. I mean, that's this scope resolution operator is useful because it's not just my superclass that I can access. I can access any class up the inheritance tree by using the scope resolution operator. So now when I make and print my chicken, I print out the animal parts. So al and age 0, those are the default arguments. So, you know, we still haven't initialized everything. Lifespan got initialized because it was protected. I had access, and then I could print out my chicken part. I'm a chicken who lays 5 eggs per day. All right, so all that to say, you know, private variables stay private. Protected, I get access to as a child, and the public, of course, I have access to, and so does everybody else. But we still, even with inheritance, we still recognize the privacy of the parent class. Questions? All right, so we have a bunch of problems we're going to solve. Oh, the other thing, so we've been announcing when we've been constructing our animals and destructing our animals, but let's do the same thing for our chicken class. Let's make a destructor. And this, of course, I don't have direct access, but I do have this public getName function that I can use, so we will getName. Okay, so let's make our animal one more time. And we can see that, well, the animal constructor gets called first, and then the chicken constructor. Then we print out the animal, and that all works. And then the chicken gets destroyed, and then the animal gets destroyed. And that is a lot like composition, right? So if I mean, we could even do it really quickly. Let's say that I no longer inherit from animal. Instead, I'm going to have animal al as a member variable. Okay, well, I can just, with a couple of quick changes here, I can just add al dot print al dot get name al. And then, well, I lose access to lifespan, right? So I had that before. I don't have access to it now because that's protected is strictly to do with inheritance. But otherwise, I have a class that looks pretty much the same. And when I make and run it, well, you can see that actually the same thing happens. The animal gets constructed first and then the chicken. And then when I print it out, well, that works out fine. I call on the animal print and then I get the animal part and then I continue and describe the chicken part. And then when I'm destroying it, the chicken gets destroyed, then the animal, right? So at this point, composition and inheritance are the same thing other than this one protected member variable. But when you're trying to, I guess, reason about, what is actually happening when I have this big inheritance hierarchy, it's composition, right? It really is, this is what's happening. There's a couple compiler tricks that make composition different, but it's not that different. All right, questions? Okay. So public and protected members can be accessed from my derived class. Private, I cannot access directly, but I can access them indirectly, say through the print function, right, which is public. We can also use friendship, right? The same way that we did with the student and the address. We can make the animal superclass a friend of ours, or the animal class can be a friend. Are we able to initialize the parent class constructor using the constructor? Yes. Well, we're going to see how to do that. So we haven't done that yet, but we're getting there. Sort of like Java Super. There is, well, we're going to see. Also, when we want to resolve some sort of a collision, naming collision, we can use the scope resolution operator. So here I wanted to call the animal print function, not the chicken print function. So I just tell the compiler, hey, look in the animal class, and call that print function. In Java, you can do something similar, but you can only access the direct parent using the super keyword. In C++, if I had a bigger hierarchy, I could go further up and directly for the exact function. All right, so member access. So if I have a base class that has private, protected, and public members, well, the private members, of course, are inaccessible in my derived class. So they're invisible, let's say. The protected members stay protected, and I have access to them, but nobody outside of my class does. The public members stay public, and I have access to them, and so does everybody else. And then on top of that, I can add more members to my derived class, private, protected, or public, as I like. And then I can go down, maybe I have a derived class. So this is the animal class. This is the chicken class. And this is just fried chicken. It's a type of chicken. Well, I still inherit all of the private members of the, super class. They're invisible to my parent, and they're also invisible to me. The protected members, well, they stay protected, right? Protected just goes all the way down the hierarchy. The public members also stay public. And then, well, what happens to these members that I've declared in chicken? Well, the exact same sort of thing happens. The private become invisible. I do not have access to them. But the protected stay protected, and the public stay public. And that's really messy, so let's look at this one, which is a lot nicer. And then I have all of these inherited, and then I can, of course, declare my own members in anywhere I like in this hierarchy. Okay. So yes, member usage, we've gone over this. The other thing we looked at is the order of the things were being constructed, and we had an inheritance hierarchy that was only 2 deep, but if we had something even deeper, so let's say we have a vehicle class, and then we make some derived classes, so a car is a vehicle, and an aircraft is a vehicle, and a boat is a vehicle, and then I want to have a specific type of car, a Mazda. So my Mazda is a car. Well, when I run this piece of code, I create a Mazda, and the constructors are all called. For every layer in my inheritance hierarchy, a constructor is called for that part. So the first constructor that's called is the vehicle constructor. The second constructor is the car constructor, and the third is the Mazda. Right? So we start with the base class, and then we come all the way down to the derived class. And that's the same as composition, right? So the contained class is constructed first, and then the container class is constructed last. It says use base class initializer syntax to call the base class constructors. We haven't done that yet. We'll show you that in a second. The other thing is that, well, when we destroy something, so in this case, I make a Mazda, it gets constructed, and then once I exit the main function, the destructors are called, and the destructors are called in the reverse order of the constructors. So my derived class constructor gets called first, and then the parent of that, and then the parent of that class, and all the way up the inheritance hierarchy. Okay, well, what happens now if we throw some contained objects in there? Let's see the order of construction. Sorry, let me think a second. Right, okay. Yeah, let's do this. Okay, so we have the same inheritance hierarchy as we did before. We have an animal, and it is the superclass or the base class or the parent class of the chicken. But now we're going to have our chicken contains an egg. So yeah, a very little rough UML diagram. So this is the example that we're going to look at now, and we're just going to look at the order these things are constructed in. So we have an animal class. Again, the same lifespan, name, and age. We have a chicken that inherits from animal, and well, we have an egg, which we don't have. We haven't included that yet. We're going to start by making a chicken called Stanley. We're going to print Stanley out and make sure everything is working, and then we will try to break it. Okay, so the animal is made, then the chicken, and then I print it out, and then it's destroyed. So nothing new yet. So let's add this egg class. So this egg has one member. It's just a string that describes the egg. So in this case, it describes the size of the egg. By default, it's a mini egg, and we have a getString function. So in my chicken class, I want to add an egg. Right? It has a default constructor, so I don't have to initialize it right away. I do want to sort of add this to my print function, so it can produce eggs. So what is it? Egg.getSize. Okay. So we know how to initialize egg if we wanted to. I'm not going to do that right now. We have a default constructor. That works just fine. So if we look at the order that things are constructed in, well, the animal is constructed first, and then the base class is constructed first, and then the derived class. But the derived class contains an egg object. And if we remember back from when we made students with the address, the contained objects gets constructed, and then the container object gets constructed. And then when we're talking about destructors, it's just the reverse, right? So the chicken gets destroyed first, and then the contained egg object, and then the base class animal object. All right. questions? All right, so we still haven't initialized the animal class, so let's do that. Just let me make sure that yeah, all right, this will do. Okay, so we have the same inheritance hierarchy, we just no longer have the eggs. So we're in P3. So we're going to make a chicken again, print it out. And we get the same thing happening. So al and age of 0, those are the default arguments. Even lifespan is a default argument. I didn't bother initializing it. The egg count gets initialized, but none of the animal parts are initialized. So we want to initialize those animal parts. Well, right, if we go back to, so we're using inheritance, but let's just say again, we switch back to composition. Well, then we know how to initialize this thing. Well, first of all, we make a couple small changes. Okay, so if we want to initialize al, well, we use the member initializer syntax. So we're going to say, take al, before you construct the chicken, construct this member al, age and what is it, lifespan. And here are the arguments that you can use, lf. Right? So when we have a contained object and we want to initialize it, and we want to do it in the most efficient way possible, we, of course, use the member initializer syntax. And then we get make P3. Yeah, so the animal's constructed. And now I have an animal that actually has the correct name, Chicky the chicken, and the constructor uses the correct name, and the age and lifespan, everything works, right? So this is what we want actually from our inheritance. So let's go back and switch this back to inheritance. Public animal. Let's take away al. Now this, let's do it this way. I don't need to use the scope resolution operator here, but it doesn't hurt. So now I have, well, and now I have this, which is no longer working, but I want to do basically the exact same thing. But how I tell it now is I use the class name instead of the member variable name, right? So it's almost exactly like composition, except now I'm just directly, I don't have a name for this variable, it just exists, but I can use the variable name and member initializer syntax and the scope resolution operator to access it. And then when I run it, yeah, I get my animal is constructed, and lo and behold, all the member variables are initialized, right? So this is called member initializer syntax, or sorry, this is called base class initializer syntax, but it's basically the same thing as member initializer syntax. I'm just grabbing the animal part of my chicken, and I'm passing in these variables so that it can be, the constructor can be called. All right, questions? Okay. So when we are making something, yeah, we did this. So this was the previous example. So when we had a container object and a contained object in an inheritance hierarchy, well, of course, the base class was made first, and then the derived class is made second, but out of that, the egg is made before the chicken, and then finally the chicken is made. And then when we destroy them, of course, it's reverse order. The chicken becomes the first thing to be destroyed, the egg is still second, and the animal is the last thing to be destroyed. And yeah, so And so how do we initialize those things in our base class? Well, the base class is essentially like I contain an animal, and I just use the same sort of syntax. Instead of member initializer syntax, it's called base class initializer syntax, but it's essentially the same. The other thing about C++ constructors and destructors is that they are always called. The constructor especially. The destructor, you can get away with not calling all of them, but that's kind of a problem actually. I'll talk about that in a second. But so every layer of the constructor gets called. So the base class constructor is always called either explicitly, right? When we called it in the last example, that was explicit, or implicitly by calling the default constructor, which was all the previous examples where we didn't initialize it properly. So how we do that is, of course, using our base class initializer syntax. One other thing to note is I've had a default constructor for this animal class, right? Like, let's take this out again. And this still works in this example, but let's say that, well, let's take out this default argument. Now, when I make an animal, I don't have a default constructor any longer. I have to at least pass in a name variable, a string, right? So what that means for my chicken class is, well, I can't make a chicken unless I explicitly call the animal constructor, right? So now that I'm relying on, here before I was relying on the default constructor, and if I don't have a default constructor, then I need this base class initializer syntax. Okay, the same when I was using composition. If my address did not have a default constructor, then I had to use this sort of syntax in my student class. If I have a default constructor, then I can kind of get away with being a little lazier. All right. Okay, so that is so far. Inheritance and composition have been very, very similar, almost exactly the same, except for protected member variables. But we get all the same. We construct them the same. We have the same access, right? Private is still private. What about inheriting functions? So we have a very similar class, but now we've added some behavior to our animal. So now our animal can go forage for food, right? It can eat for, go find food for some number of minutes or find food for some number of hours. Now this is, these are two functions with the same name. This is function overloading, which we have not explicitly, I've referred to it a few times, but so you can't do this in C, right? In C, this is not allowed, but in like Java and C++, it is. And the idea is that, well, if I have the same name for two functions, as long as the arguments are somehow different, in at least one sort of way, right? Then the compiler can tell them apart, because when I call this function, I supply arguments, and it can look at those arguments and say, oh, he wanted this function, or she wanted this function, or whatever. And so I can overload these functions. I can have two forage functions that are almost the same, except for the arguments that I pass. And in my chicken, well, I still inherit from the animal class, and I'm overriding the print function, but I didn't override these forage functions. I can just inherit them, right? So here I make an animal Al and a chicken, Chicky the chicken. I print them both out, and then I can have them both forage for food. And in this case, Al, of course, can forage for 20 minutes, but Chicky the chicken can also use these animal forage functions. Let's go here. Okay. So at feeding time, the Al will forage for 20 minutes, and Chicky will forage for half an hour, and then forage for another 30 minutes. It's a really hungry chicken. Okay. So that is really, and if I'm using composition, I don't get that, right? So this is really what inheritance gives us. In my base class, I have public functions, and I get to use those for free. I get to call them on my chicken object. So this is where sort of composition and inheritance split a little bit. I can always, yeah. All right, so let's say that, well, that's great to have that forage behavior, but my chicken wants to forage for, my chicken's a little hunter. You know, they're little savages. I don't know if you've ever had chickens, but they will eat anything. Anything that crawls or walks or moves that's smaller than them, they will gobble it down. So this one is going to forage for a certain food type. It's going to go hunting. Forage. And I have, I'm overloading this function again, right? It's still forage, but I have a different parameter. So this, you know, is sort of legal. I'm going to steal some of this code. So this is now a chicken. I have to use the get name. We'll forage for, let's say, hunt for food type. Okay, so now my chicken has its own unique forage behavior as well. Okay, so let's go here. Right away, we have a problem. No suitable constructor exists to convert from float. So this worked before, but as soon as I add this forage, I tried to overload the forage function in my chicken. Now the compiler is saying, well, I don't know how to change this float into a string. So this is a problem. And here it's saying, I don't know how to change this int into a string. So now when I call forage, the only forage that the compiler sees is this. And this is one of those decisions, like, people say C++ is complex, and sure, it is. But to me, it's not, I kind of like it. I don't know, it makes sense to me, right? The decisions they made make sense. Except every once in a while, you have just sort of out of the blue some rule. I'm sure there's a very good reason for it, but I don't understand what that reason would be. But as soon as I try to overload this function now in my derived class, I can no longer access my base class functions, at least not directly. All right. Well, let's make sure that we can forage it all, first of all. Forage. Let's forage for, it's going to go hunt some mice. And let's make sure that works. And yeah, chicken hunts for mice. So that works, and my animal still forages the same way it always foraged. But for some reason, I lost access to these, at least directly. But I still actually do have them. I just have to tell the compiler, hey, look, if you go up to the animal class, there is this forage function. Like, I know I confused you by overriding it, but trust me, there's these functions there. And so I still have that inherited behavior, but now I have to call it directly. I have to use the scope resolution operator. And again, I don't understand why that should be necessary. I'm sure there's a very good reason, but it's sort of like C++ is sort of like English, right? It's old, which means it has a lot of sort of competing ideas in it. And in English, like, there's a lot of rules that make sense. And then there's once in a while, there's just a rule that you just memorize because it doesn't fit anywhere. And it's just, for whatever reason, that's how the language evolved. So this is one of those rules. I feel like I don't really understand why you have to do this, but you do. So, all right. Questions? All right. So yeah, and also that is where we diverge from composition, right? So when a chicken contains an animal class, I don't get to inherit those functions. I mean, I can make my own functions and then forward those calls to the animal class, but that's arguably not the same thing. So yeah, so in this example, if I have an animal that can run and then I have a hyena that runs at a certain speed, well, if I want to call the original run function, I have to use the scope resolution operator because the compiler gets confused. Okay, so that brings us to the different types of inheritance. All the inheritance we've looked at so far is public inheritance. This gives us what is known as the ISA relationship, although we haven't really described what that is yet, but we're going to right now. So if I use private or protected inheritance instead, it's not technically an ISA relationship. And in fact, it's a lot like composition. And so often private inheritance gets used as a substitute for composition and delegation. We'll talk a little bit about that. So remember back to public inheritance and access, member access. Well, my private went to invisible and my protected stayed protected and my public stayed public. Well, if I switch now to private inheritance, right? So now I am privately inheriting. Well, these private member variables are still inaccessible to me. But now what I'm saying is that all of the members that are coming from the base class can be at most private, right? They cannot grant any more access than private. So that means my protected members become private in my derived class, and my public members become private in my derived class. And we will see a use case where this is actually useful behavior. And then, of course, on top of that, I can add my own members. So in private inheritance, private becomes invisible, protected becomes private, public becomes private. I can go down another layer, right? I can have a derived, and now these are both using private inheritance. And now, well, of course, it's inaccessible here. It remains inaccessible in my derived object. The protected and public members become private, and those become inaccessible 2 levels down in my inheritance hierarchy. And then, of course, private becomes invisible, and these 2 become private. And then I can add more things to it. Okay, so that's, and oh yes, an honorable mention, but doesn't get used as often as if we have protected inheritance. Well, it's the same sort of idea. Everything can be at most protected, right? I cannot inherit anything that I assign access greater than protected to. So private, well, that stays inaccessible. The protected stays protected, and then the public gets mapped to protected. And of course, we could go down extra levels if we wanted to. All right, so what is this ISA relationship we keep talking about? Well, ISA relationship is really if I have the same public functions, right? If I can make the same public calls on an object, then I have this ISA relationship, so to speak, right? Obviously, there's some type stuff going on with the compiler, but for instance, for my goose to be an animal, or for any animal, has to speak. I have to be able to speak. So if I have an animal, a reference to an animal class, I should be able to call speak on that animal. And that is sort of the definition of what an animal is that it implements this function. Which means that if I do something like this, my class goose, if I privately inherit from animal, well then in my goose class, this becomes private. Which means that if I tried to do something like this, well, of course, the compiler's not even going to let you do that. If I use public inheritance, I can do this, right? Then my goose is an animal because I can refer to it using an animal pointer, and then I can call speak on that animal pointer, and my goose will say something. But we're using private inheritance. This is now a private function. So I lose that behavior, which means that I lose that ISA relationship. So private inheritance is actually a lot closer to composition, right? Because when I have a private member variable, all those functions on that member variable are inaccessible. So yeah. All right, so questions on that? Yeah. How the what? So this, Yeah, well, because the compiler won't let you, but the reason why the compiler does not let you is that because this will not work, right? So in my goose, if I privately inherit from animal, this speak goes from public to private, which means that, well, even if I said goose G, and then I say G dot speak, that's not allowed, right? This will give me a compiler error, as we're going to see actually an example of that. But now my speak function is private in my goose class, which means that, so sort of the definition of this is a relationship is that, well, a thing is, it's sort of like an interface from Java, right? When you define an interface in Java, you say public functions that you should implement. And these are also the public functions you can call. The is a relationship has everything to do with the public functions. Yeah, hopefully, I don't know. Do you want to clarify anything or? No. It will stop you here, right? Because then this just becomes and again, it's not really, it's just, this was a decision made because when I say, we are on purpose allowing polymorphism, right? So we're allowing general handle to point to a more specific, like I'm allowing a base class handle to point to a derived class because I know that if it's a derived class that it inherited these methods, right? So I know that Goose has a speak function if this was a public inheritance. Yeah. And so if I have an animal, I'm expecting that that animal could speak. Like that's the contract. An animal can speak, and if my animal can't speak, well, then it's not really an animal. That's the, hopefully, I don't know. Maybe we'll go through the example, and maybe that'll help too. So we're going to use private inheritance to solve a problem. So we're going to make a stack, right? So we've talked a lot about function call stacks. So a stack is simply, well, I have a push and a pop operation. And if I push a number on, then it goes on the stack, and then maybe I push 4 on there and push a 2 on there. And I'm drawing it bottom up. If you draw left to right or whatever, it's up to you. But the key is that now, if I want to remove something from the stack, I call pop, and pop always returns the last object that was added, right? So if I'm drawing my stack upwards, it's going to take the top item. So if I call pop again, it removes a 4. I can then call push, and it'll push another number on, and then push and another number, and then I call pop again, and it always will return the top element, or the last element that was added. Okay, so we want to make a stack, but we're feeling pretty lazy today. So we're going to use the vector class, right? So vector is a container from the standard template library. And we're going to just take advantage of stuff that was already written. So I'm going to go vector C++. And we see here c++.com, which is a pretty good site, and CPP reference, which I think used to be pretty good, but now there's a lot of ads on it. I don't know. One of these had a bunch of pop-ups, which I didn't really like. They used to be very good. Let's go with this one, c++.com vector. So yeah, this just gives a description of the vector class. Here's some implementation details, or at least some contract, right? Like, oops. Did not mean to do that. But also, I have this list of functions. So for my stack, I want to implement this interface, right? So I want to be able to push an int, right? We're going to store integers. I want to be able to push an int onto the stack. I want to be able to pop it off and return it at the same time. And I want to be able to, well, ask if it's empty, right? So if it's not empty, this returns false. And if it's empty, it returns true. And so I want to use my vector. So, well, let's see here. Well, we definitely have an empty function. So that's pretty good. Tells us whether the vector is empty. So we directly have something we can use there. Pop, Push. Well, we have a push back. Let's see what that does. Push back adds a new element at the end of the vector after its current last element. Okay, so that sounds like something we can use there. We have pop back and deletes the last element. Okay, we want to delete the last element and also return it. This returns a void, so there's actually this other function here called back. Returns a reference to the last element in the vector. So using pop back and back, we can simulate the pop and push. What would we call that? Push back. We can use for the push. All right. So here is one version of a stack class. We're going to solve using public inheritance, implementing this interface. So public inheritance, I'm going to publicly inherit from my vector class. Vector is a template, which means that I have to supply a type, or if I don't supply a type, that means that stack also has to be a template, which we're going to get to later. But for now, we're just going to inherit from a vector of ints. And then we're just going to implement everything right here. Let's give this a name. And then we're just going to forward this call to pushback. All right. And then, so yeah, that should work the same. That's what we wanted. Pop. It's going to be a little different. We want to store the element first, and then we can call pop back, which just deletes the element but doesn't return it. And then we can return temp. Good. And empty. Well, there's an empty class or an empty function that does exactly what we want. We could just take it away, but I'm going to, well, first of all, I guess I could make it const. I'm going to be a little explicit unnecessarily and just say return. And again, I'm going to use the scope resolution operator here to say, please call the empty for the vector class. Okay, so that is my implementation of a stack using these vector functions that I inherited. And then the vector takes care of, the backing array and everything like that. These we don't, that's fine. We don't need that. All right, so we're going to make a stack. We're going to push a bunch of numbers on it. So from inaccessible, right. So the one thing I forgot is that these should be public. All right, so by default in a class, they're private. So now they're public. So to test my stack, I am going to push a bunch of numbers on from 0 to 20, or 0 to 18, I believe, counting by twos. And then I'm going to pop them all off, right? So this should test all three of my functions. So while it is empty, pop everything off and print it to the console. Okay, so pushing 0 through 18 on there, that's great. This is the order they went on. And then it's a last in, first out data structure. So the last one on there was 18, and that's the first one popped off, followed by 16, followed by 14. So great, it's behaving just like a stack. That's fantastic. However, we do have a problem of this. I mean, I don't really care about this, but I can do something like this. Well, I can't really see it here, but yeah, because for some reason but yeah, I can access something from the middle of my stack, which, okay, maybe that's not a big deal, but I can do this, right? And if we look at this, this is just, well, you can see this is just a function, right? The subscript operator is just a function that I can, pass in an argument to. And here I'm going to assign location 5 the value 200. And the reason I can do that is because that function is public, right? That subscript function is public, which means that now I can just sort of change one of the values and I ruin my stack property, right? This may seem like a trivial property, but it's really not. Stacks are very useful, right? Not the least of which is the function call stack. That's so yeah, I have these public members. In fact, I have all of these public members, which I really kind of don't want them there because somebody can use them to mess with my stack property. So I don't want somebody to accidentally change my stack into no longer a stack. I can make stubs for all of these, right? Public, but I can override them and just leave them empty. But that would be a lot of work to do all of these. So I don't really want to do that either. So public inheritance, not a good solution. Even though it works, we're exposing a lot of functions we don't want. So yeah, questions? Okay, so let's solve it again, but now we're just going to solve it using composition, right? Well, we saw how similar those were. Inheritance and composition. Except for you don't inherit the functions. So let's private. Let's make a vector of ints called vec. All right, so now this is going to be very similar, except I no longer have a function, but my member variable does, so I can just call it. And here I can, so everything is being stored in my vec member variable. But we saw, in terms of memory, that's not that different from inheritance. And yeah, so now we have a new stack. It does exactly the same things. We did some minor changes. We now access our member variable. Let's go down here and change this to a stack 2. And whoa, look at that. Right away, of course, there is no function that matches this. Well, it's saying it's looking for the brands and the operator. There is a built-in subscript operator. Does not match because argument 1 does not match the parameter. Huh. I guess there is a generic function, but it's just not, it does not work for our stack class. That's interesting. But the important part is that no longer works. So I no longer have this danger of somebody abusing my stack. And when I run my stack, of course, it behaves just like a stack, the same as it did before, which is great. Last in, first out data structure. But now none of these functions are public. This is private member variables, so nobody can access them. All right, and this is a good solution. In fact, probably, I would argue the best solution, not because it's the most efficient. You can squeeze a little more efficiency out of private inheritance, but it is the easiest to understand, right? This is very easy to understand, that's a very good thing. Especially when you're debugging, right? It's not just reading code, it's debugging it and trying to figure out, well, where is this and that? And yeah, so this is a good solution, but it's not the only solution. Questions on that? All right, 38. So let's look at the last one. We're going to use private inheritance here. Well, basically we can use all of these. Should work. Because, well, I'm calling these functions, but only from inside of my functions. They're private. I privately inherited them, so they went from public to private, so I have access. So this should all still work. And indeed it does. Everything behaves the same as a stack does. And if I try to ruin my stack property, well, now it says this is an inaccessible function. So the function is there, but it's private, right? So there's this operator, but it's a private operator, so we cannot access it from outside. So I've effectively sealed off my, I've inherited all these functions, but they are protected from outside users. Now this is, as we know, as we've seen, this is basically the same as composition, right? And really in terms of efficiency, I would argue, depending on the compiler implementation, but these are probably the same. This is no better or worse than composition in terms of, I'm still forwarding the function call here, and even here. The one advantage of private inheritance, why it gets used, is that there is this extra thing you can do. So I'm just sort of forwarding this empty call to the vector empty call, but I can do something. Don't need the return value, do I? I might need the scope resolution operator. I'm not precisely sure of the syntax, but I think it goes something like this. Right, so I don't need the argument list or the, do I need the argument list? I don't need it here. And if I put it here, I think I get an error. But I can say basically, well, I inherited this public function, but I actually want to keep it public, right? So I can just say, like, just use the regular vector empty function, and we can see that everything still works. So private inheritance is used, and I think the big advantage over composition is that I can take and leave as much of the public interface as I like. I can just say, well, use these as public, but keep the rest of them private. So I can selectively inherit, so to speak. All right. Questions? All right. I-41. All right, so our last little bit of inheritance, we will may or may not get through the whole thing. But of course, well, we've seen this in Java. We see this. Sometimes we want something to wear more than one hat, so to speak, right? So in this case, we have what's called an RV, a recreational vehicle, which is in some respects a house and in some respects a vehicle, right? You can drive it around, but it also has like a fridge and stuff and a bed. So we want our RV to have aspects of both of those things. In Java, you can't do multiple inheritance. You have basically a parent, and then you can define an interface, which is actually, I mean, works pretty good. I have no complaints about the way Java did this. Interfaces are fantastic. But in C++, we can actually have two parent classes. So while an interface, actually, I don't even know. I think the rules have been updated, right? I think you can include an implementation in an interface now. You just can't include member variables. But that could be wrong. But in C++, we just go, well, whatever. I don't know. This is a class. This is a class. You can inherit from both. Go crazy, right? Do what you like. That does introduce a few problems, though. The main problem is the diamond hierarchy. So let's talk about the types of multiple inheritance. So this is one type of multiple inheritance where we have two distinct base classes, or the inheritance hierarchies of the house and vehicles never intersect, right? So in this case, there's really no problem. I inherit everything I want from house, and I inherit everything from house and everything from vehicle. And then if there's collisions, we use the scope resolution operator to resolve them, of course, if there's naming collisions. But yeah, so that's one thing that can happen. The other thing that can happen is, well, let's say I want, I'm running a school, and schools have students, and I have a base class of person that has like a, name, address, whatever. Well, also my school has employees, and I want to have some salary information for those employees, but they are also people. So they also need a name and an address and what have you. And so then I have a grad student who is both an employee and a student. And so I inherit from both of those, but lo and behold, if I go up the inheritance tree, I have the same class in both branches of my inheritance tree, right? So this person class is repeated twice. And so what happens here? Well, if we, this multiple inclusion base class means that person is included more than once, and what happens is that, well, I get two names, right? And so we'll see an example of that, but of course, in this particular example, that's probably not ideal. You really don't want to have two different names, although maybe that could be why some of you have more than one account, right space, but so what we really want from here is this, right? So yes, a student is a person and an employee is a person, but if I happen to inherit from both student and employee, then I want the compiler to just use one version of this person, right? And then both student and employee can inherit from that person, and then I only have one name for my grad student, which makes a lot more sense. So this is called a virtual base class, and this problem of multiple inclusion base class where I have two of the same class is called the diamond hierarchy problem. The reason why it's called that is, of course, this in some sense forms a diamond. And yeah, so the solution is to use virtual inheritance. So this is when people talk about multiple inheritance and how complicated it is, this is the thing that introduces that complexity. This is sort of a simple example. Of course, inheritance hierarchies can be much bigger. But let's take a look at all of those. We got 10 minutes, huh? Can we get through it in 10 minutes? Let's see. We'll have to do WooClap tomorrow, or Thursday, I mean. Let's cheat. Let's cheat a little bit. So I have an animal class, and it just has a name, right? And that name is public. It's just going to make our life a little bit easier. But I also want to have a human and a horse, and I'm going to cheat a little bit. So let's make a human that inherits from animals. So I publicly inherit from an animal. I have a constructor that, of course, takes a name that I use to initialize my animal, because there is no default constructor. People also have some number of arms, right? So in this case, by default, we have 2, but we initialize that as well. Also, another type of animal is a horse. And horses have some number of legs, generally 4. Oops, num. All right, so we have a human that's an animal and a horse that's an animal, and we can build one of each of them and print them out. So okay, so now this is sorry, I really dislike it when it's all crowded like that. So let's add a little bit of well, that's not going to be not the prettiest thing ever, but so in my animal constructor, so I construct my animal and then my human is constructed, and then I construct the animal part of the horse, and then I print out both of their names, right? They're public, so I have direct access to them. Okay, well, let's, I don't know if you guys are up on your mythology, but there's this mythical beast, which is called a centaur, which is a human-horse hybrid, right? So we have the upper body of a human and the body of a horse, and so we have 4 legs and 2 arms and a tail, and so that's called a centaur, and we're going to make one. So we want to inherit from both our horse and our human. So no longer animal, we want human and public horse. Oops. Okay. Well, animal is no longer our direct parent class. So actually, we don't want to do this anymore. In fact, we want to call we have to call the horse constructor because, well, uh, int num arms equals 2 and int num legs equals 4. So yeah, we have enough to initialize all of the parts, a name. Okay, so we're going to initialize the horse part. And the human part. Right, both of those constructors have to be called because they do not have any default arguments, or they don't have any default constructors. And this, if you can just really ignore the ugly formatting. So yeah, we make a centaur, and when we make a centaur, we call the horse and the human constructor. And well, it's Centaur Bob. That sounds like a fun creature. We see already we have some problems. All right, so Centaur name is ambiguous. Okie dokie. Well, let's just make Centaur Bob first of all and see what happens. So what happens? Well, I call the animal constructor for my human part. So animal constructor is called, then the human part is built, and then the animal constructor is called the second time, and the horse part is constructed, and then Centaur Bob, the centaur constructor is called. And then, well, we can see that, so I made 2 of my animal parts, and this says now that, well, this is ambiguous, which means that I have 2 animal names, so let's disambiguous it. Again, the hero of the hour is the scope resolution operator, so I can say, well, I know my horse part has an animal, and I know my human part has an animal. I guess this is human. Human part, this is the horse part named, right, so using the scope resolution operator, I can say, look, I know there's 2 names there, but just grab me the one from the human part, and then grab me the one from the horse part. Shared, right? So yeah, the human part is named Bob, the horse part is named Bob, and I can even go as far as to say, well, these are public. I can say Bob dot horse name equals Mr. Ed. And then I can print out those 2 names again. Shouldn't have started this, but oh well. So if I just change the horse name, we can see that the human name stays as Bob. So here they're both named Bob because, well, Bob is what I passed into both of the constructors here and here. I just passed in this name. I could have passed in something different. And then I can directly access the horse part and say, well, change that to Mr. Ed, and the human name stays the same. And so what we have in this example is the multiple inclusion base class. This is the animal part. And we have 2 animal parts, one from our human half and one from our horse half, and they both have a name. And we can access them individually. And that's fine. And actually, maybe in that example, it works, right? Because a centaur has a human name, and maybe they have a horse name for when they're talking to horses. So that might be what we want, but often what we actually want is something that looks like this. So next class, we will look at how to do this. It's too bad we, anyway, I hate interrupting in the middle, but yeah, we'll finish this off next class. So we're going to figure out how to do this and sort of what are the consequences of it. So yeah, that's it for today. I will see you guys on Thursday.